Hello, this is the first video in a two-part series titled From Patterns to Interactions. In this series, we'll explore the math and science behind animating physical systems. This video is about the Ising model. The Ising model is a simplified mathematical model of ferromagnetism. When these materials are cooled down, a phase change occurs as the system goes from a disordered state to an ordered one. Microscopically, the magnetic spins start clustering, and magnetization occurs spontaneously, without the influence of an external field as thermal equilibrium is approached. To understand this effect, let's define this system. First, we'll create a grid that is n units long and n units wide. Now, we'll give every point in the grid number either 1 or -1 at random. This will correspond to its spin state, which is either up or down. We can visualize this using a grayscale color map. That is to say that 1 is white while -1 is black. For each point in row I and column J in the grid, we'll assess its current spin state, whether it is 1 or -1, as the value sigma current. The spin states of the neighbors above, below, to the left, and to the right of it can be summed as the value sigma neighbors. The energy of this point is equal to -J over 2 times the current spin times neighboring spins. J is a coefficient that tells us how strong the magnetic interaction between the system's neighbors are. We want to define what the energy of this point would be if we flip the spin. This would make the final energy -E and the initial energy E. The change in this energy, final minus initial, through simple math would just be -2E. We want to flip this spin if it results in a decrease in energy or a step towards thermal equilibrium, represented by the following equations. Finally, we want to impose periodic boundary conditions. This means that the neighbor of a point at the corner will have an up neighbor on the last point of its column, a left neighbor on the last point on its row, and a down and right neighbor at its normal spots. This is necessary to avoid edge effects, as we are simulating a microscopic phenomenon, so its theoretical scale boundaries should be infinite. Topologically, this torus model provides a good intuitive picture. For those of you that are interested, the steps we just highlighted is known as the Metropolis-Hastings algorithm. It is within the class of Monte Carlo methods, as it provides random sampling while driving a system towards a constraint using selection parameters. In our situation, these selection parameters are an approach towards thermal equilibrium and minimizing the system's energy. We want to perform this algorithm over all the points in the grid for multiple iterations to produce the following animations. Keeping track of the system's energy and average magnetization can allow us to verify how effective our algorithm was at driving the system towards its selection parameters. It is clear from the graph that our algorithm drops the total system energy drastically and keeps it decreasing throughout time. It is also converging the spin states over time. We can perform this algorithm for steps across a given temperature range to evaluate the effect the temperature has on the system's stability and certain thermodynamic variables. For example, let's look at the specific heat versus temperature. You'll notice that there is a distinct peak. As the system approaches critical temperature, the specific heat graph's slope goes to infinity. How similar is this graph compared to other experimenters? The first graph is selected from a textbook titled Monte Carlo Methods in Statistical Physics by Newman and Barkma. The second graph is selected from an article written by the Institute for Particle Physics Phenomenology. These are two credible sources from the field, to say the least, so I don't think that we did that bad. One key difference, however, is where the critical temperature is. You'll notice that others have a critical temperature closer to the accepted value of 2.269, while mine lies at 1.3. This is most likely due to small normalization errors, but the general physical picture is still demonstrated. But what exactly is this physical phenomenon? Why is specific heat so high at this critical temperature? To explore, let's look at the system's magnetization over the same temperature range. This graph shows the phase transition clearly. When the system gets hotter, the energy is not just raising the temperature, it is used to change the system's configuration, like unaligning the spins, shown by the decrease in average magnetization magnitude. This change allows for more movement, as the kinetic energy affects how the molecules vibrate, move, and rotate. It's worth noting that as the lattice size gets larger, this unalignment process happens much faster, resembling the almost instant process that we see in real life as the critical temperature is approached. But how did we do compared to other experimenters? The following graph is taken from a paper written in the European Journal of Physics. Not that far off. The main difference again is where the critical temperature lies. This, as we noted, was due to some normalization differences. Before I conclude this video, I would like to make a few suggestions for the future of this project. For one, utilizing a lower-level, statically typed computer language like C or C++ would greatly benefit the long computation times associated with this project. Maybe even rendering a real-time animation might be interesting as well, just as my previous double pendulum project had, and an upcoming one in this series. I would like to thank all of you for making it to the end of this video. The animations used were generated in Python. I've linked the program in the description for those of you who are interested. That being said, please like and share this video. Subscribe if you've enjoyed and would like to see more of this type of content. Goodbye.